Okay, hello everyone. Let us continue the third part of today's class. Okay, in the second class we have talked about since spatial multiplexing uses multipath scattering to increase throughput, the lower line of sight throughput gain numbers are expected. Okay. Perhaps more interesting, however, is that the throughput increase is as large as it is in line of sight conditions. Conventional, that is the traditional wisdom, has assumed that MIMO would not be effective in line of sight conditions. However, these results suggest the benefits of MIMO may be realizable in a broader range of conditions than has often been assumed. Okay. Moreover, we can go back to the table 1.6 and see this table again. For the TPS, transmit power savings. For the line of sight transmission, the average value is 10.5. And for the non-line of sight transmission, the average value is equal to 9.2. So these two values tell us that MIMO saves more power than SISO. Any questions? If you do not have any questions, then we will go to a very important section, which also may be a little bit difficult for you. Section 1.9, Review of Matrices. Matrices and vectors arise naturally in the study of MIMO communications because of the use of multiple antennas. For example, if there are multiple transmit antennas, then at any instant we can represent the set of signals applied to each of the antennas as a vector S. S is equal to S1, S2, etc. to SNT transpose. Here NT is the number of transmit antennas. Similarly, the signals at multiple receiver antennas can be represented as a receive vector R, which is equal to R1, R2, etc. to RNR transpose, where NR is the number of the receive antennas. Furthermore, because there are NT by NR combinations of transmit and receive antennas, each of which can be viewed as a separate communication channel, it is convenient to represent the overall communication channel in a MIMO system as a matrix with NR by NT elements. Please note that the MIMO channel matrix is NR by NT, not NT by NR. Don't be confused. Using matrices and vectors greatly simplifies the mathematics needed to describe the behavior of MIMO systems. As a result, in order to be able to read and understand the MIMO literature, it is necessary to be conversant. What is conversant? Please see the handout. Okay, page 205. Problem 1. What is conversant? Solution. Conversant is an adjective. Definition of conversant. 1. Having knowledge or experience used with. For example, conversant with modern history. Another example is conversant with the operating system of the computer. Second, archaic, having frequent or familiar association. 3. Archaic, concerned, occupied. Okay, so when we say be conversant with, we can say be familiar with matrix nomenclature and matrix properties. This section lists those definitions and matrix identities that are needed to understand the material in this course and the majority of published papers on MIMO communications. No attempt is made to prove or elaborate on these properties. Thus, this section is intended to be a reference only. Okay, you should be able to prove the following property after you take the course, or after you have taken the course, linear algebra. The student who wants to delve into matrix mathematics in greater detail should consult a text on that subject. Two excellent references on matrices are those by Horn and Johnson. Okay, please see reference 38. Okay, reference 38. Oh, sorry, I put it in the wrong page. Okay, this page. Okay, reference 38. Roger A. Horn and Charles R. Johnson, Matrix Analysis, Cambridge University Press, 2nd edition, 2012. Okay, I have this book. And next, okay, let us go back to the slides. And Carl Mayer, reference 54. Oh, sorry, the wrong page again. Okay, I will fix this problem later. Okay, reference 54, Carl D. Mayer, Matrix Analysis and Applied Linear Algebra Book and Solutions Manual. SIAM, Society for Industrial and Applied Mathematics, 2001. Okay, back to the slides 207. Okay, let us go to section 1.9.1, basic definitions. Okay, A identity matrix. An n by n square matrix with all diagonal elements equal to unity, that is equal to 1, and all other elements equal to 0 is called an identity matrix, and is denoted by IN or just I. B transpose operation. The transpose of a matrix A, which we denote by A transpose, is defined as follows. A transpose Ij is equal to Aj. This notation means that the element of A in the jth row and in the ith column, okay, of A, that is, the transpose of a matrix is formed by replacing its columns with its rows. C trace. The trace of a square matrix A is denoted by TR of A and is defined by TR of A, which is defined as the summation AII, that is, the sum of all the diagonal elements of a matrix. Okay, the orthogonal matrix. A real square matrix A, that is, a matrix with real elements, is said to be orthogonal if A times A transpose is equal to A transpose times A and is equal to C times I. C is greater than 0, where C denotes an arbitrary scalar. A matrix is said to be orthonormal if C is equal to 1. Hermitian operation. The Hermitian of a complex square matrix A is denoted by A Hermitian. By definition, A Hermitian Ij is equal to A star Ji, where A star denotes the matrix A with all elements complex conjugated. The Hermitian operation is also called the conjugate transpose of a matrix. It follows that A Hermitian is equal to A. Okay, it is very easy to prove. A matrix A is said to be Hermitian if A Hermitian is equal to A. F unitary matrix. A square matrix U is said to be unitary if U times U Hermitian is equal to U Hermitian times U and is equal to C times I. C is greater than 0, where C denotes an arbitrary real scalar. If C is equal to 1, U is said to normalized unitary. In this course, as well as in most of the MIMO literature, the term unitary implies normalized unitary. Hence, C is equal to 1. The definition of unitary is analogous to the definition for orthogonal, the former applying to complex matrices and the later to real matrices. G. Frobenius norm. The norm of a matrix is a generalization of the concept of vector norm, which in turn is the length of a vector. Similarly, the norm of a matrix is the measure in some sense of the size of that matrix. There are different types of matrix norms. However, in most of the MIMO literature, the Frobenius norm is commonly used. The Frobenius norm is defined in one of two ways. We denote the Frobenius norm of a matrix A using the two nomenclatures below. Okay. If we write two vertical lines A and another two vertical lines and a subscript F, it is defined as summation I, summation J, and the absolute value of Aij. Okay, that is the sum of the absolute values of all elements of A. Okay, if we write two vertical lines A and two vertical lines with subscript F and a superscript 2, okay, it is defined as summation I and summation J and the square of the absolute value of Aij, that is the sum of the square value, the squared of the absolute value of all the elements of A. H. Linear dependence. A set of vectors vk is said to be linearly dependent if there exists a set of scalars ak, not all zero, such that summation k ak vk is equal to 0. Okay, please note that this 0 is in boldface, so it is a vector here. I linear independence. A set of vectors vk is said to be linearly independent if the vectors are not linearly dependent. That is, vk are linearly independent when the only solution to summation k ak times vk is equal to 0 is the trivial solution ak is equal to 0 for OK. J rank. The rank of an m by n matrix A is defined as the largest number of columns or rows from that matrix that form a linearly independent set. The maximum number of rows is equal to the maximum number of columns. We denote the rank of A by R of A. If m is smaller than or equal to n, then 1 is smaller than or equal to R of A, and R of A is smaller than or equal to m. Similarly, if m is greater than or equal to n, then 1 is smaller than or equal to R of A, and R of A is smaller than or equal to n. K singular and non-singular. A square matrix A is said to be singular if its determinant det of A is equal to 0, and is said to be non-singular if det of A is not equal to 0. Since the concept of determinant is not defined for a non-square matrix, the concept of singularity only applies to square matrices. L. Eigenvalues and eigenvectors. Given a square matrix A, then the polynomial in the independent variable S formed by determinant of Si minus A is called the characteristic polynomial, and its roots are called the eigenvalues of A. Alternatively, the eigenvalues of A are the values of lambda that satisfy the equation AV is equal to lambda V for some non-zero vector V. Okay, please note that non-zero. The vector V is said to be an eigenvector of A corresponding to the eigenvalue lambda. M determinant. There are multiple ways to define the determinant of a square matrix. For the purpose of this course, we define the determinant to be equal to the product of the eigenvalues of the matrix. The following additional comments apply. 1. The determinant is only defined for a square matrix. 2. The determinant of a matrix A is denoted either as det of A or as the absolute value of A, or we should call this a vertical line, A and another vertical line. Both notations are used in this course. N null space. Given an m by n matrix A, the null space of A, which we denote by n of A, is defined as the set 1 by n vectors x such that x times A is equal to a 0 vector. In other words, n of A is the set of all solutions x to x times A is equal to a 0 vector. O Kronecker product. Let A be an m by n matrix and B be a p by q matrix. It follows that the Kronecker product A O times B is the mp by nq block matrix. Okay, what is the block matrix? Let us see the handout. Okay, page 228. In mathematics, a block matrix or a partition matrix is a matrix that is interpreted as having been broken into sections called blocks or submatrices. For example, the matrix P is equal to 1, 2, 2, 7, 1, 5, 6, 2, 3, 3, 4, 5, 3, 3, 6, 7 can be partitioned into 4 2 by 2 blocks. P11 is equal to 1, 2, 1, 5. Okay, these four 1, 2, 1, 5. And P12 is equal to 2, 7, 6, 2. Okay, here 2, 7, 6, 2. And P12 is equal to 3, 3, 3, 3. Okay, here 3, 3, 3, 3. And finally, P22 is equal to 4, 5, 6, 7. That is 4, 5, 6, 7. Okay, the partitioned matrix can then be written as P is equal to P11, P12, P21, and P22. Okay, let us back to the slides. Okay, so the mp times nq block matrix A O times B is equal to small a11 times B, etc. Small a1n times B, and so on. Finally, small am1 times B, etc. and small amn times B. Okay, next, let us look at the section 1.9.2 Theorems and Properties. Okay, A for any matrices A and B, A times B transpose is equal to B transpose times A transpose. B for any matrices A and B, A times B star is equal to A star times B star. C for any matrices A and B, A times B Hermitian is equal to B Hermitian times A Hermitian. D for any matrices A and B, A times B inverse is equal to B inverse times A inverse. E for any matrices A and B, the rank of A times B is smaller than or equal to the minima of the rank of A and rank of B. if the determinant of any identity matrix is 1. Okay, it is 25 minutes. Let us take a break.